Hello, everyone, and welcome to another episode of Solving Advent of Code in Rust and Try to Learn Rust in Between. I'm Eugene.
Luciano, hello.
And Roberto.
Thank you for following along. Now, if you never did Advent of Code, it's a code challenge that's published every year in the Christmas period, so around December. Right now, we're working on last year's challenges. There are 24 challenges in total. You can find them at adventofcode.com, and we might show a banner with that. We're publishing all of the code that we do on GitHub, so it's all open. We're very open to suggestions or PRs. So if you guys have any ideas or anything that you see and you'd want to suggest, feel free to go there, check it out, and open a PR or put comments or do whatever. There's also a link in the description of the Twitch channel, so you can click there if you want to see it. Now, last episode, we started on problem number 14, which I'll share my screen right now. There we go. Essentially, we'll go through the README. The problem, the exercise 14 or challenge 14, as you want to call it, is basically applying a bit mask to some numbers. I can read through it. I suppose that's, but I'll skip the wordy bits because we've already gotten started on it. Essentially, we will receive an input made up of instructions. We can get either a mask, which is basically a bit mask. X's are bits that are to be ignored. Ones or zeros are bits that we have to alter with the value in the mask. The other type of instruction that we can get is a memory and an index and the value. The idea is that we store the number here after applying the mask at a particular index in a list. Obviously, the input is a bit larger than this, but the program is always supposed to start with a mask. The masks are always, I think, 36 characters long. So the bit mask is always given as a string of 36 bits. There are a few examples here which basically explain what we're supposed to do. We receive this value, which is basically one of the ones at a memory allocation point, so 11. Oh, this is actually the 11 example. So this is the value that we receive. This is the mask that we have to apply, which is the one defined on top. And this is the value that we're actually going to store in memory. As you can see, where we had a 0, we now have a 1. And we apply this to the number that we store. Same here, we had we had a 1. The mask specifies a 0, so we apply a 0 to this, storing it at the index here. The X's, as I said before, don't do anything, so all the numbers, all the bits in all the other positions are completely ignored, as in we don't touch them, we just store them as they are. There are another few examples, but I wouldn't go through them for now. I'd suggest we go through the code that we did last time. We only got started on this towards the end, so we didn't get very far. So far, we just have an enum for the instructions that we get. It can be a mask, which is basically the bit mask defined before, or a memory address where we're going to get a value and an index to store it at. We have this parser here, which, again, we built somewhat quickly. We're picking if the string starts with mask, we've noticed that all of them in input start with this particular string. We pick the relevant mask and we store that in the enum. Else, if it starts with memory, we're picking the address that we need, and then we're picking the value from it as well. The only other thing that we did was we collected all of the instructions in a vector. I would actually want to run this right now just to make sure that it works on my machine, because I think Roberto did it last time. So let's quickly run and see if it outputs anything here.
Yeah, you must see a list of commands. Yeah.
Cool, it's perfect. We have memory, we have masks, we have everything. So I think the best way to start on this, so basically what we have to do now is actually store the mask, apply the mask, and start storing values in memory. I would try doing this in a naive kind of way, if that makes sense. Like have vectors maybe for all of this? What do you guys think?
Yeah, I think we need to figure out where to decide on two details. One is how are we gonna store, let's say, the memory or represent the memory, because we have an understanding that there are like cells with an index, and every cell can contain different numbers that we might need to change over time.
Yeah.
So we need to figure out how to model all of that. And the second thing is when we have that mask, we'll need to have a way to convert that to either a number or multiple numbers and then do bit-wise operations, or naively, like character by character, convert with the other number. But that means we need to do the opposite to convert the number into bits. So yeah, I think we need to decide either one or another approach.
Okay. So
to store the memory, the best approach is using a map of integers to integers, because
that's what I was thinking.
They can be overwritten. It's a sparse matrix because obviously we don't have to allocate a vector of the maximum length that we find, also because we don't know what is the last and the highest address when we start. It's just a streaming of information. So
map new, does this work?
No, it's hash map, and I think we need to import it from STD collections.
I think it already did it for us. No, it didn't. But there you go. Now it did. Hash map new, and I can even define it here, right? Which is going to be U64 and U64.
Yeah. And new is a function that you have to call.
I think so. So you need to give parentheses.
I had it and then I deleted it. And this should be. Does it need to be mutable?
Yes.
We have to add stuff to it. So yes.
Yeah, I would say so. Okay. So
did it actually import collections STD for you at the top?
Yeah, it did.
Okay, nice. Oh, but it also either map, which we don't need.
Okay, so the imports look good for now.
Now we can go 4 on top of every instruction.
Yeah. Do we actually need to collect them here? I don't think we do, right? Anyway, so I'm thinking if we go, whoops. Like this? No.
Yes, yeah, that would work like this, yeah, not like Python.
I think we can skip the collect if we do this, right? Because this is going to iterate through it.
Not sure, actually.
Doesn't this work as a generator?
We can try.
Let's
Let's try that.
Yeah, probably you have to change the type at that point that we have.
Yeah, because we can probably. The type is not gonna
remove it, and then remove also the type in line 28.
Yeah,
and see if it just guess it.
Map
of lines. Oh my god, what is this?
No, okay, we'll keep collecting it. We'll look at this later.
Collect is fine.
Okay, so for instruction in
now we have to match and differentiate if it is an assignment or a mask change.
Instruction, and I will actually cheat and look at one of the old exercises because I forgot the syntax for match.
We can help you.
Yeah.
Yeah, this is matching a string. We have to match an enum.
The enum is basically the name of the enum. What did we call it? INSTR, right?
Yeah.
Yep.
So you can say INSTR : mask.
Mask, and then we do something.
And then you do the fat arrow after the instruction. And then you use the curly brackets, and you need a comma also in between cases.
But do you have to use the curly brackets or not?
Not necessarily, only if you want to have multiple instructions. Also, the other thing is that we need to...
the round brackets, sorry, I was talking about the round brackets.
We need that because we want to essentially explode the values that are inside every variant, right?
Okay.
So for instance, mask has only one string, so you can call it mask, for instance, inside like an argument inside the parentheses. You can say mask or M or whatever you want to call it, and inside your curly braces, then you can reference to the current string that way. While memory will have the two
address and
value. So yeah, exactly.
Okay. All right, fair enough.
So when we find a mask, we have to just store it in a mutable current mask.
Right.
Then we can initialize it outside of the loop.
Exactly.
The current mask, line 35, you can put it outside of the loop.
You're absolutely correct.
Yeah. Now is because that's a pointer to a string, and we have a string. It's a pointer to str, and we have an str. Declare current mask as a reference to a string. Can we do that? Let mut, because it's mutable, current mask.
Yeah.
Of type reference to a string with the capital S. And don't assign anything there, just...
Oh, no, you need to assign.
I don't think it's going to be too happy with it,
if you don't want to assign it, you can do like an option and then assign it to none, which, it's a little bit more boilerplate.
It found struct string, so it's
It's complaining if we do this? Yeah. No, it's just...
No, it's not. It's happy enough. But I don't know if we want to give it a reference, though.
Okay, it's fine. The reference is completely fine. Why not? We have the string in the parsed section. When we parse it, we generate strings and we keep it there. Then we just reference to them. There's no need of copying them around.
Yeah, the idea was we could consume it. But we can't consume it because we are currently looping through it. Cool, fair enough. So this is simple. We don't actually need the curlies, right? If we just do that. And this is where the complicated stuff happens.
If we want to go for a naive approach, so like you say, they want to do the naive approach, we can just, every time we have a value to change, because we have val, and we have to change it, setting some bit to 0, some bit to 1. So what we can do is looping on top of the mask here, from right to left, if possible. So
I think there is a reverse, right? No, there isn't. There was a trick that we used before for looping in reverse, but I don't remember.
.rev, I think we use. But we need to do .iter.
It does to be, yep.
And I think you cannot do .iter in a string. You can do .chars to get like a list of chars, basically.
It's not happy with this, but...
Try to do .iter after chars, maybe?
No. I think it's not... No, it doesn't.
Oh, no, wait. It's working. It's just that we need to continue and do more.
Okay.
So right now it's taking that as a return statement, and it doesn't like it.
So we can map over it, I suppose? Or what was the suggestion, Roberto, basically?
The suggestion is starting with a mask with value 1. I use 64 with value 1. Then for each character starting from the right. Well, we can start from both sides, but okay, let's not talk about this. Then do an if the char is an X, we do nothing. If the char is a 1, we have to set that bit to 1 in the value. So we have to keep a mutable value somewhere.
Okay, so essentially for each, right? And then
if it is a 0, we have to set the bit to 0.
Value, maybe something like this. So this, but this can't be a lambda, right? Can you have
multi-line lambdas? Yes, just open curly braces.
Okay.
Before this line, we have to instantiate 2 variables. One is a let mutable value equal to val, because it started to that one, then the mask is changing it to something else, so must be mutable.
Yep.
And we also initialize the mask.
Why is it unhappy? This match types. I don't think it likes this.
No, I think it was just loading.
Mask does not live long enough. So I would just do this.
I think
mask just not live enough. But he's inside the
and this is going to consume it, right? When we get the chars.
No, we don't have to consume it because we have to apply the mask multiple times. We just have to go over it.
No, I think it's fine. I think chars doesn't consume.
Okay, so now it's unhappy that this doesn't live long enough.
Yeah, because we are basically... So the reference to that mask is created inside this match block, and we are trying to assign it to somebody that is outside the match block.
Yeah, so that's why I was thinking we could just pass it. Can we clone it?
I guess you could, but then it's not a reference anymore. I mean...
But mask can't give us, instead of the string, a reference to the string that is already in the instruction.
I think if you put the ampersand inside the parentheses, that might happen.
Okay.
Let's see.
Now it's unhappy here. Expected struct string. And found reference.
So we have a suggestion here.
All right. Let me take a look, because it was on a different...
And then there is another suggestion. You can use mem replace in case like this, which is something we've never done before. So it could be interesting to have an example.
I'm not certain what mem replace does. So
I think own value, I suppose, means that we create a string rather than a reference. And yeah, we reallocate it, and then we own that value.
Okay.
I think this is my understanding, at least. Instead, this one is probably a smart, well, not smart. It's probably a function that behind the scene is going to do some memory swapping, like low level, changing the memory for you.
So the idea would be that we're replacing current mask with this.
Replace, not repal.
Typing is not my strong suit. And I need to import the package,
We might need to import it, yes. Yeah. It might be std mem, I suppose.
Hang on, it should be in the, std mem, correct. Okay, so we're just going to do it, or meme. Okay. Destination, expected mutable reference.
Again, we are again with a mutable reference. I hate that.
Because this, hang on, because that was still there.
Yeah, there is this one. Remove current underscore mask equal question mark.
Wait,
what? Sorry, let me come.
From the memory replace. Before memory replace, you have current mask equal. It's not needed. Because mem replace is returning.
Because we're doing the mem replace. Yeah, I understand now.
It's doing in place.
It does
it
in place as opposed to.
And now we have to declare line 34
so
current mask as mutable.
Mute.
No, I think it wants the mutable in line 34.
It's not very happy with this, is it?
Go back to just mask.
Look at this, ampersand mute.
Okay, cool. I'm completely lost. This is great.
So it needs to be a mutable reference, I think.
So let's go back and look at what... Actually, I got more comments. And unmute. Yeah.
Yeah, I think the suggestion is that in line 34, current mask is a ampersand mute string, right?
Yeah, probably.
Or not. Or is this one the suggestion?
Or I'm not actually getting... As we said at the start of this, we're not very good at Rust yet. So
yes, thank you.
If for now we just go
thank you
cloning the
very
string
much for the suggestion.
and solving the problem, then we look about
mismatched types, expected mutable reference.
No.
So
because current mask
mismatched types, okay. Font ampersand.
But if for now we just go with cloning the string and
and then we'll revisit that at the end.
And we go on with the algorithm, and then we look at the memory allocation to make it more efficient.
Would it not have been easier to just pass it the value up top? And that's it.
What do you mean?
Thoughts?
By passing the value.
You're muted, Luciano.
No, he's not muted.
Or I can't hear you.
You can't hear us.
Hello.
Still can't hear you.
Okay, we are certainly talking.
Yeah, for sure.
It might be my headphones. If that's the case.
It was your headphone. 1, 2, 3.
Oh, I can't hear either of you. Ah, okay. So probably have an issue with my laptop.
Perfect.
I don't actually know what to do. I'll try another set of headphones. Sorry.
Sure. Take your time. In the meantime, Luciano, probably if we go to a string and we just copy there and then we look at memory allocation.
Is completely gone. Okay, I have to leave and join back, restarting the whole thingy. Sorry.
No problem.
You are the only one with the code. We are waiting for you.
Yeah.
The idea was just clone the string. For now, we know that is shit because we can just keep a reference to the string and loop on top of the reference. So we are locating memory for nothing.
Mm-hmm.
But
yeah, I agree with that. Even though the suggestion here is that memory swap will do what we wanted to do. It's just that we use replace rather than swap.
So it's swapping two pointers, memory swap. Okay, so pointer logic.
So we can try this one as Eugen is back. By the way, thank you, Shirskak. I hope I am pronouncing it that correctly. Very good suggestions. And also we have...
I can now hear you. Hello. Again. I'm sorry.
Welcome back. Right. So we were saying, other than thanking everyone that is participating in the chat, that basically the suggestion was to use memory replace, but in reality the function we want to use is memory swap, which is probably doing what we want. If that's still too complicated, probably it's fine for now to just clone strings and make it work, and then we'll revisit and make it more memory efficient.
So it's still not happy with any of this.
Let me add your screen again. Should be visible.
Right. Okay, back to us.
So memory swap, which takes
I think current mask is already a pointer, so probably you don't need the ampersand. Then they probably need to be mutable references. So probably you in line 34, you probably need to use ampersand mute on the right-hand side. No, sorry, on the other side of the
But I'm
column.
Not defining it as anything. And
so it's ampersand mute space string, yes.
All right, gotcha.
And now
and that is fine. And now mask must be...
Is ampersand mute, yeah. Okay, cool.
It's not happy with this, though.
No, because it's passing us a string, not a mutable something.
Yeah.
Right, I have no idea how to solve that. Unless you can specify ampersand mute. Let's go back to strings and we revisit this in a second time.
Instead of swapping, leave it like this. Try just to do current mask equal reference to mask again.
Sorry. Okay. Current mask equals AAA. Mask equal mask. Like
reference to mask.
Reference, apologies.
No, here we are back to the lifetime problem, right?
Yeah, no, you need to do dot clone. You need to do something like dot clone and then remove all the references, basically. Like they become just mutable values, owned values.
Yep.
And there you just need a comma rather than a semicolon because it's
yeah. Okay.
Now that mut you don't need anymore on the right.
There are too many mutable now.
Okay, this is a little bit of a hack for now.
Yeah, this is dirty, but let's go on. I was saying before the loop in line 39, we need the value that we are going to mutate, changing the bits, and the mask. The mask starts at 1.
Yeah.
Let mutable mask of type U64, because we have to do all the maths in U64.
It might figure it out on its own, but let's see.
Equal 1, then if we figure out on its own, is better.
Should be, I think. Yeah. No, I32.
By the way, quick break for a second. We have Mr. Halsey that is just raiding us. And by the way, it's a channel I follow a lot, so I'm really happy that he's here. He's doing streams of a project where he's building like in Rust Cloudflare workers to have like a CMS on static pages, which is pretty cool. So yeah, thank you for the raid.
Nice, thank you very much. That's very cool. All right, so what were we doing here? So we have a mask that starts with 1.
The character is, let's start with our logic. If the character is 1,
yep,
it's not conflicting name with type.
Might be.
C is enough. Come on. C is the universal variable for a char.
Okay. Do we want to do a match on this?
We have to match 0, 1, or we don't care. If it's an X, we just do nothing.
Yep. I'm just thinking it might be easier, right? Because then we have 0. Actually, this is going to be a char, so it should be like this, right?
Probably.
Or should it not?
Or is that go?
Haha. I wish I would
remember. The comma.
Yep, coming right up. Okay, so if it's a 0 or it's a 1, we
if he's a, you can put an underline, because if it is an X, we don't care.
Yeah.
Okay, let me do another quick break, because we are getting this question a lot in the chat. And I'll do a super quick recap. So basically in this channel, we meet once every week to do Advent of Code, just as an excuse to learn Rust. So this is just one of the many exercises from Advent of Code, specifically the number 14 for last year, so 2020, which is kind of an interesting bit mask CPU operation related one.
Could maybe show the README just for everybody who joined recently. So the task at hand is we receive inputs like this. They're essentially instructions. It either starts with mask, which is going to give us a sort of a bit mask, which is what we were trying to store earlier in that loop. And then there's instructions of storing different values run through this mask at different, let's say, memory addresses. The mask applies to the value, to the binary value, basically. So in this example, they're actually going through the first memory thing that they're doing, which is the value 11, represented here in 36 individual bits, the mask, which contains X's, 1s, and 0s. In the case of an X, we don't alter the value at all. In the case of a 1 or a 0, we alter the value by the value that's there. So if the mask contains a 1, our binary representation will have to contain a 1. If the mask contains a 0, our binary representation will have to contain the 0 at this particular bit location. So we were doing a bit of a naive representation of this.
The dirty solution.
The dirty solution. Just loop through everything and go, yeah, for character X, do Y, basically.
Yeah, we are reparsing the mask every time we have to set a value. There is a better solution, but we are doing that later. Yeah. So now, if it is, I was saying, if it is a 1,
do we care about default? We don't.
The default is just underline. I don't know what is happening if you match and is an X and you didn't take X in account. Is
the match need to be exhaustive, so Rust
is going to complain. The underline.
Yeah.
Okay, so
the underline.
But it was underline default, right?
No, underline. No, just underline.
Just underline.
The little arrow. Yeah.
The fat arrow.
Yeah.
Okay.
Yeah.
And nothing to do. Okay. Again, if it is a 1,
there's an error already. Borrow of possibly uninitialized variable current mask.
Yes, because it's possible. We know that in our instructions there is always a mask before the first assignment. But if there is no, if there is an assignment before the mask, it can be unsigned, and Rust doesn't know that our put 36x.
So that's 5. This is 10, 20, 30. 1, 2, 3, 4, 5, 6. Great. Nothing beats typing
and
X's
you need to
by
do
hand.
to string or string from.
String from or to
string from.
Double semicolon. Sorry.
What? Double colon here.
For the people watching, you can tell that most of us come from JavaScript. So.
Yep. Which may or may not be very obvious at this point, but yeah.
In the match of the 1,
you
there do the value. There is or equal in my Rust, so the pipe equal. No, value pipe equal. Not dot. Remove the dot. Pipe equal.
Pipe equal.
Mask. Semicolon.
It is a thing.
So this is applying the mask as an OR to the value, and in this way it will set the bit to 1. Okay. Now for the 0, due to the fact that we are parsing, is a little bit more tricky. It is if.
Okay.
The value and only one end, because it's a bitwise end value and the mask. Okay, if the value and the mask, then it's different from 0. I think with my Rust is fine.
I think it's going to let's
be verbose. Okay.
Be specific. It's probably going to suggest. Oh, unused parentheses. Yeah. Right.
Unnecessary parentheses.
Correct.
Okay.
That is correct.
Now, if this is true, value XOR equal. I don't know how it is XOR equal in Rust. Is it probably
the caret? I think
caret equal.
Probably.
Let's try. Let's find it. There we go.
Mask.
Yep.
So basically, if it's a 0, that we have to set a 0 the current bit. We check if the current bit is not 0, and then we XOR with the mask. If it's already 0, we have to do nothing. Now, outside the match, after the match, we have to shift the mask by 2, by 1 bit, so multiplying basically the mask by 2. Mask, no, inside the loop.
Hang on.
Inside the loop, there. After the match, inside the loop. We can do mask star equal 2. That basically is shifting the semicolon. Is shifting the bits 1 to the left.
Yep.
Then after all of this, so after the for each, we have out of the for each, we have to set in our mask a hash map that is called mem.
This was add. It wasn't add. It was something else.
To set inside the hash map is not with the square brackets, no.
No, I don't think so.
Luciano, that's Python.
Yeah, sorry, I was looking at the chat. What is the question again?
Hash map. How do you set a value in an hash map with the square bracket?
You need to do dot set, I think.
Dot set. It wasn't dot add.
Or dot insert.
Insert sounds more. Yeah, insert it was. Okay. And key and value.
Yeah, and our modified value that can be equal or can be different. This is absolutely inefficient. You are lacking a semicolon on line 52, probably.
Yeah, that is correct.
This is extremely inefficient, but probably it's working.
Well,
quick thing. We had another comment saying that in line 34, since we are using string from, there is absolutely no need to also declare it as a string explicitly. So
absolutely correct. No, that was left from before when we didn't initialize it. Good catch. Thank you. All right. So what was the expected return for the thingy? It's probably adding something together, right? The sum of all values left in memory after it completes.
So the sum of all the value of the hash map. So in Python will be sum hashmap dot values. In Rust, I don't know.
There might be a way to get an iterator of values, and then we just call sum.
See. Roast hashmap iterate values.
Meanwhile, there is an interesting question I'm going to try to answer, which is doing string new without the 36 excess. Would it work? I think practically yes, because we know the input, and we know the input always gives us the first line is going to be the mask. So even if we just put a placeholder string, the first instruction will replace it. But this is a little bit on the safe side, because if we had other values, we would have a mask already that works, and a type of mask that is not going to mutate the values until we find a real mask. Yeah. So I think both approaches work. This one is just a little bit more generic, I think.
Yes.
Yeah, it's defensive. I'm not sure what it's upset about now.
Because we're not value.
I removed the return. Okay, cool.
Yeah, now.
So from what I can see, you can do a for loop over a map as long as it's mutable.
Yeah, but there is not a sum of all the value of a map. No.
If you can iterate over the values, then you have sum on iterators of numbers.
We can go. Yeah, but it's iterating over a tuple, basically. So it's giving you the key and the value. So just
no, there is into values you can use.
Oh, it's not map, it's mem into values.
Or just dot values if you don't want to get. I always struggle to remember the difference between into something and the straight version. I think has to deal with references.
But these one are integers, so I think there is no difference with integers.
I don't think it matters. So you were saying there is a sum.
Yeah, exactly. So that should do it.
Yeah,
that's the good answer. Thank you, and Muleman. Into
use of
takes
unstable library.
Hang on, what?
Also.
Sorry, too many.
Into consume the variable. Well, it's fine if we consume it. But he's complaining about some unstable stuff.
Yep. Unstable map into keys values.
Try to just use values.
Yeah, let's see. It's happy now.
Okay.
Okay, let's run the test and see if this even works.
How does it explode? Okay, perfect.
Unused mem. Oh yeah, because we're not doing that.
Mem and then we didn't use it anymore.
Correct.
What is thread current?
I don't know because I didn't import it. It's the joys of using Visual Studio Code. It just imports stuff.
Your Visual Studio Code is too aggressive.
Yeah, it's like, let me just write this for you.
Okay, run again the test part 1. Now, if he's happier. What? Yep. It's a shitty solution because it's super slow.
That was terribly slow.
We can improve it.
Yeah, let's have.
Do you want to throw a commit with a comment first naive solution?
That's actually a good idea. Sorry, I removed the comments and stuff.
Yeah.
Is there anything else commented? No. Cool. Committing now.
You can throw in a commit with first naive solution so the people from home can look at the commit history and see the first stupid solution.
Sorry, git pull, git stash pop. Just making sure I'm up to date. Naive solution for year 2020 example exercise 14.
By the way, the reason why we couldn't use that into values is this one, because it's still an unstable feature. So you need to have a flag to say that you want to use unstable features.
Question that I have: the unstable features are the new features that will come, not the deprecated ones.
I think yes, it's like experimental for possibly in the future. Like they're not reliable. Maybe they're not gonna make it in future version, but I think the goal is to test them. Please, chat, correct me if I'm wrong.
Okay, understood. Thank you. Okay, let's not fight with current mask and mask because there we are going in the rabbit hole of lifetime assignment. Let's start with the easy first optimization, that is computing the stuff for the map just once instead of 100 times. So to do that at the level of current mask, line 34. Current mask is a line 34.
Okay.
We have to create two masks. One is the OR mask and the other one is the AND mask. The OR mask starts.
They're both going to start out the same, I think.
No, the AND mask must change nothing, so they must be 36-1.
So, wait.
So, the OR mask starts at 0. Now, the OR mask is an integer, is a U64 integer.
Yep. Okay.
That starts at 0.
So, 0.
Because if you take a number and you OR the number with 0, the number doesn't change.
Yep.
That is the... Instead, the AND mask must start at 36-1, because when you do an AND of a value with all at 1, the number is not changing. To do that, the fastest way is doing 2 to the power of 36 minus 1.
To the power of, which is done somehow in Rust, I don't actually know.
Me neither, so...
I'm Googling it.
Luciano, do you know how to do...
I don't know if we can use, like in JavaScript, asterisk, or if there is a function like mat.power or something like that.
It's base.pow.
Pow, okay, yeah, here we have it.
Pow patrol, yeah.
Okay, so it's number.pow patrol. So what did you say? Sorry. What? 2 to the power of what?
36, because we have 36 bits, minus 1. Because we want that number that come out.
And this is also
U64. Everything is, we are using U64, everybody, because we have 36-bit is not fitting in a U32, but is fitting in a U64. Now it's complaining because...
Wait, doesn't work on U64?
You must specify...
Check it out. Whatever mute temp is 2, and I think
it's not mutable. It's just a.
It's hang on U64 and a semicolon.
And probably it's not needed to be mutable.
No, it's not.
Okay.
Well, let's just call it 2. Just.
Makes sense.
This is something we should sort later.
So we had to do open brackets 2 as U64 close bracket dot pow.
Probably
36. Oh my god. Okay.
Now let's just leave it like this for now.
There
was another suggestion here that maybe it's a little bit.
2 underline U64. What is 2 underline U64?
I think you are saying use the 2 as a literal, but also with this type. Because it might be ambiguous when you just say 2 can be
remember the one, Eugen, remember the minus 1 or we are fucking up everything.
Yeah, absolutely. I was just curious if it works. Interesting that 2_U64 is a thing.
Yeah, that's magical syntax.
This is new.
Yeah.
But it's cool though. Nice suggestion, thank you.
So, back to us.
Yeah.
Now, when we find the mask, we don't have to store the mask, so line 34 can go. Yeah. When we are finding the mask, we have to compute the new AND mask and OR mask.
Yep.
Quick break. There is a lot of activity in the chat. One that I like to highlight is this one. And I'll make sure this will be in the YouTube description when we upload it to YouTube. But basically, it's a link that explains what are the naming conventions, for instance, into what does it generally means to and as, which is something that we have been seeing frequently, and sometimes we are a little bit puzzled on what's happening behind the scene. So that's definitely something to check out. Thank you, Mr. Alzi.
Thank you very much. That's going to be super handy. So we'll need to take a look. Okay, so this current... Wait, this is memory. We'll deal with that later.
39. Yeah, 39. Okay. Now, we have to take our mask, going in the mask this time left to right, so we don't have to reverse it anymore. And we have to compute the human and mask and or mask. So before doing that, in the line above this one, out of the loop, we set end mask and or mask both to 0.
Okay. Or mask equals 0.
Okay. Inside the loop, so in the for each.
Alphabetically, I'll do them here alphabetically as well. Yes.
Okay, sorry, we will.
Go.
Okay, there. Okay, we do the end mask and the or mask must be shifted by 1 bit, so star equal to both of them. So we take the current mask, that is the start empty, and we shift it by 1 bit, and then we choose what bit to put in the entering session. So now, if we have to do the match, we have to do the match. What?
Match over C, yeah.
Yeah, we have to do the match over C. If it is a 0, sorry, if it is a 1, well,
it doesn't matter. We'll need to handle both cases. Sorry, just copying them from there to make sure that my
here is the tricky part. Let's just put 1. Don't put in line 46 for now.
Okay.
Because it will be different. So if it is a 1, it means that in the OR we have to put a 1 because we have to move the bit that we are in to a 1. So if it is a 1, the OR mask or equal, because we are setting the bit, the first bit, or no, not star, or, so the pipe.
Pipe equals, yeah. Sorry. Gotcha.
So the first bit will become a 1. Remember that this got shifted every time that we loop. So the current bit become a 1. So when we will mask with OR, the bit will become 1. The other one is tricky. I don't know if with a match we can do it. The other one is if the character is not a 0.
If it's an X. So this
one. You can do an underscore. So you are catching all the other cases.
Yep. And we'll need this as well at some stage.
But the underline is catching also the 0 or not?
No, because I specified the 0 up here.
Yeah, but not specify the 0.
Yeah, exactly. I think Roberto is suggesting that this specific case is valid for both 0 and X, right? Exactly. So we can just use an underscore.
Okay, yeah. Gotcha then.
Okay, no, it's sorry, it's a little bit more tricky. Now, okay, I'm redoing this to explain better. Now, if it is not a 0, if it is a 0, we have to put a 0 in the end, but there is already a 0 in the end, so we don't have to do anything. Yeah. If it is not a 0, so if it is a 1 or it is a X.
Yeah, but then don't we want to have the 0 case where we do nothing? Because it's easier that way.
Let's put the 0 case where we do nothing. So
right?
So I can suggest 2 things. One is that we don't use the match and we just do if-else statements.
Yeah, we can do with that if it's easier to read.
Or there is another suggestion here, which is match guard, which, if I remember correctly, means that in a match statement on the left-hand side, you can also say if some statement. But I think just using if-else for now, it's clear enough, and then we can refactor later.
So back to our logic. If it is a 1, the OR mask must have a 1 in the current bit. If it's not a 0, okay, then the end mask must OR with a 1 again, or equal with the pipe equal 1. Okay. In this way, we are setting the mask from the single mask that we have
But-
with 0 indexes. We are creating 2 masks.
There should be an else if though.
No.
Because
It's not
the
an
case
else if.
of-
No. It's not an else if. It are 2 different if, because they work on 2 different masks.
Yeah. Okay. Cool. Gotcha. Correct.
Because C different from 0 is also true when C is 1. So they are 2 completely different if, because one if
because we're
is doing the
controlling 2
logic for
masks.
the OR, and the other if is doing the logic for the AND.
You're right. We're controlling 2 different masks.
Yeah. Now, instead, in the mem, it becomes easier. The code in the mem is way easier.
So
because you can just go back to the mem insert.
Yep. When we can get rid of all of this.
Yeah.
Key stays as it is.
Value is val.
Oh yeah, you're right.
And the AND mask, and OR the OR mask, obviously. But
So-
and OR the single one, the bitwise. And the AND mask, and OR the OR mask.
Yep.
If we did everything correctly, in this way we are parsing the mask only once and not at every time that we have a memory instruction. So it's faster.
Let's see. So it was
Question before you run this, because I think I might
Yes.
have missed something. How do we move the position of the current element? Do we shift
42,
somewhere?
42 and 43, we are shifting.
Yeah.
Oh, okay.
The mask get shifted by 1 bit every time we enter in the loop. We enter in the loop with zeros, so shifting zeros, you have the same. Then we choose if we have a 1 or a 0 in the first bit of the mask. And when we go back in the loop, we move everything by 1 bit and we set the new bit, or not set the new bit, because when you do this shift, we multiplying by 2 is coming in as a bit to 0. We just have to put it to 1 based on our logic. That is the logic from our mask.
Yeah.
Would it be equivalent to use the shift operator?
Yeah, it could be equivalent, but I don't know if in Rust, do you have the greater angular equal 1? I don't know. Do you have
Okay,
it?
let's run the test and then
Let's see if
meanwhile
it
I'll check
runs.
that.
Okay, let's check if it's working, because
And let's see if it's faster, because the original was 1.7 seconds. 241. This is slower.
But finish it in 0, so in the line below. I don't know which time you were looking at. I think this is faster. But if you want to do a commit, going back, we can add the benchmark later. We have benchmark. I added benchmark last time for the exercise 13 that probably Luciano we can show after this. What do you think?
So
if we have time, yes.
If we have time,
let me stash it.
Oh, by the way, we are doing the usual mistake, which is, are you running the tests in release mode? No. We are just running the test.
Yeah,
so
but
it's also 0-0.
Okay, well, but to compare times,
we'll check them later. Okay, cool.
We check them later. Yeah, we don't care. This solution is also getting rid of the problem of copying the memory, because now we are setting integers, so we don't have to copy the string around and stuff like that.
By the way, I think we can use the shift operator is like in C with the major, minor.
Equal. Okay. So line 42 and 43, Eugen. Instead of the star equal, you can do no, the other one. Less.
Less and more.
Two less. No, two less.
Two less. Oh yeah, because
and two less equal 1.
Do you need the equal?
I think so. Otherwise, we have to assign back to the variable.
Okay, let's see if that works.
And this
same
should be the same, yeah.
Yeah, but with the 1, not a 2, because otherwise we are shifting 2 bits.
Let's see if it runs and if it passes the test. I mean,
I think from on the CPU level, the shift and the multiplication. The multiplication is a special case of the shift. Multiplication is implemented by taking all the bits of the stuff that you have to multiply by, doing a lot of shift of the original value by that bit, the bit that are at 1, and then summing them together. So in the end, the multiply by 2 and shifting by 1 bit for CPU level is the same stuff.
Okay.
Yeah, I would expect also Rust to be able to optimize.
Yeah, Probably Rust CO, you're multiplying by 2. Let's do a shift that is faster. I don't know. Based on the architecture, can be faster or slower.
So I would make a commit with this that we have right now.
Then we can try to add benchmarks to it. And we can add benchmarks. We don't commit the benchmarks, so we can jump between commits and we can compare the 2 commits times.
Yep. Optimized solution. Better solution. Crap. It doesn't matter. Sorry. I'm really not good at typing stuff today, and thankfully you cannot see my terminal.
Yeah, we can see your terminal. If you're not using the one in VS Code,
I am not. Sorry.
Your scenes are just for you.
Meanwhile, I'll show another couple of interesting things that were happening in the chat. For instance, if you want to get the biggest number ever, you can use, for a type, you can use the semicolon max. So that, I don't think it was useful here, but it's something that can be useful.
Our dev and talk code say that those are numbers at 36 bits. Obviously, we don't have a U36, so we are simulating it with a U64, but we just work on the first 36 bits.
The other one is this one. So there is, other than power, there is power I, which I think is the exponent, which is integer. So it's that might have been useful as an alternative to doing that underscore U64, I think.
You start from the exponent and then you give it the base, basically. Or is that not what it is?
No, I think it's just the difference between power and power I, where I think
what is the difference?
I think it's the type of the argument that you are passing.
But the one there I think is readable and it was working. So
I can check. By the way, thank you for the follow, everyone. We had a few. So Brookzerker, USDCB, and Mr. Alzi. So thank you very, very much.
Elgin, go in the exercise 13. You will find a folder called benches, yeah.
I guess the idea is to add a similar one to exercise 14, right?
Yes.
I will do that the lazy way, and then we can work on them.
You have also to go in cargo TAML of the exercise 13 and look at that there is a couple of stuff to copy. The dependency
and the bench.
Yes.
So I can confirm that hypothesis. And here Brookzerker is mentioning that, like, if you look at the documentation, you can see, for instance, you have pov I, which means the argument you are passing is an integer, and you also have pov f, which is a float. So depending what you want to do, you can also use different functions to get different types of exponents.
Okay,
interesting. Presumably they are quicker.
Yeah, and the interesting thing is that they are implemented directly on the type. So it's not like a library that allows you to take a base and an exponent, but on that type you use it as a base, and then you have different function depending on what type of exponent do you want to use.
So for instance, they optimize.
Yeah, for instance, in JavaScript, you would use mat.power and then pass 2 arguments. Here is, you already have that function in the type.
Elgin, now if you can open a terminal in VS Code, because we want to see it this time.
Shit, I'm not sure how.
Command Shift. Okay, you did.
Found it.
Okay, go in the exercise 14 folder.
Let me see. 2020 exercise 14.
And try cargo bench. See if it's all. You saved the file, yes?
Yeah, I did.
Okay, now if for the first time you run it, is going to install dependency.
Exactly.
This is the new npm install.
Yeah, this is the new npm install.
Fair enough.
Because from what I understood, there was a bench inside Rust, but it got deprecated, is unstable. They basically tell to not use it anymore. And this criterion is one of the suggested way of doing the benchmarks.
All right. I did read a bit about it when you added the benchmark for the previous exercise, but I didn't go very deeply into it. It seems to be very complete.
Yes, we are just doing very stupid stuff. The only stuff to point out is the black box function, but we will talk about it later.
Okay.
Yep, come on, install, please.
It's doing its best. I should turn off all the internet consumers in my house. Like take my phone off Wi-Fi.
No, I think it's more building than downloading there.
Yeah. Fair. To be honest, since I changed the router, my internet has become much better. So, yeah, if you think your internet service provider is bad, it might just be that the router they gave you is bad.
Which, yeah, I think is very common.
Yep. That's not to say I'm not going to change them anyway, because you can get more for less money, but that's a topic for another day.
Our crappy connection, yeah.
Yeah, exactly. At least it's expensive, you know.
Come on, Rust, you can do it.
It's stealing it.
Come on, Carlo. It's 7. Just for time. Luciano, do you have some stuff to put on the screen while we wait? No, okay, move it on.
Not anymore. I used all my tickets.
I'm sorry. Well, maybe you can actually walk us through, Roberto, through how the benchmarking stuff works while this is installing.
As you can see, there is not a lot of code. There is you have to specify in the cargo toml the name of the file. Okay.
Oh.
Started.
Hang on.
Okay, warming up is doing the warming up. Is doing this stuff. Is running it a lot of time. So. Because to have reasonable numbers. Okay, we have reasonable numbers. We are around 186 microseconds, more or less. Try to check out the previous commit.
Yep, let me, from here, right?
Yeah, you didn't commit this code, so you can check out. Okay, don't do that.
Yep.
Don't do that. Leave it like this. Now I think you can check out the previous commit, and it's not going to complain.
Hang on. Git log. Yeah, naive solution. Cool, we're good.
We are on the naive solution. Okay.
Cool. I am on the naive solution, so I can run cargo bench.
Yeah, run cargo bench again. We were 100, then I forgot.
You'll see it in a second now. 186.
Okay, let's remember that we are there.
186.
Okay. Warming up. Doing stuff. Okay, you see that you also have the delta in percentage. This solution is 40% slower than the previous run.
Nice. Well, not nice.
Okay, so, but we say
it's a nice improvement.
We started with the naive solution that was slower, but I was thinking it was more slow than just 40%. Then we went to the optimized, I think, solution that is 40% faster than this one. So, and in this way, we also did.
Quick thing: does Criterion store previous executions?
Somewhere.
Yeah, that's interesting. I didn't expect to see that plus 40%.
Me neither. It might store it on your machine, like somewhere.
I hope I don't see your machine. But probably
I don't see anything else.
In your home, in some .something file. To be honest, I didn't took a look. It's weird.
I don't know. Could be interesting. Not in this use case. Maybe for a library, for something a little bit more sophisticated. That if you have that in your CI pipeline, if it can remember the previous commit or master or whatever reference, you can have an interesting.
Depend on how your build fleet is done. If your build fleet is an SSH instance that is always on, is always the same, yes. If your build fleet is a pod, Kubernetes pod, no, because the pods get killed after the build.
But
so
maybe
you have to store
it.
Maybe there is an option to store it somewhere, like a S3 DynamoDB table, stuff like that. And that
or
point
just
you have
even
the history.
It could even output to a file which you can check into your repo, which is simple enough. And it can always run with a previous reference in mind, basically. So you'll know when you merge something in your...
An amazing question. I don't think we're going to do that. I mean, not now, but it could be very interesting to do that.
To have a flame graph of the call to see what is the slowest call and try to optimize that. Yeah, I don't know how to do that now. We can prepare something for next time.
We should keep this in mind for next time because it might be a cool exercise, as in it's useful stuff to learn. Okay, so I should be checking out origin main.
Yeah, then we can comment the benchmarks.
But we kind of proved our theory that of course the bit shifting is much faster.
Yeah, because why? Because instead of parsing the mask every time that we have a value, we parse the mask once. We keep the mask stored as integers that are faster to use, and we end and or every time we apply the value. Also,
for every memory assignment, we do only 2 instructions rather than changing every single bit, basically.
Yeah.
So 36 changes against 2, I think. Yeah, 2. It's much better.
Okay. It didn't add.
Oh, this is pretty cool. There is a crate called Flame Graph that is pretty easy to use. We'll need to test if it works on a Mac, but yeah, that's pretty cool.
I will test if it works on a real PC. No, I mean, sorry.
We can test it on a Mac. Roberto can test it on a PC or Unix.
Ubuntu.
Why doesn't this push?
Did you detach somehow?
No.
Yeah, you are like on a branch, which is...
Jesus.
You are in the detached head.
Check.
Git checkout.
And I lost my commits.
You made a mess. Perfect.
Woohoo, great. It's fine. I'll fix it after.
Wait. You still copy this file before closing it.
This one?
Yeah.
But this is already committed.
No, it's deleted. It's not committed. Well, it's not a lot of code, to be honest.
I can save it here because it's no big deal. Okay. All we have to do is add this back into...
Yeah. It's very similar to the 13.
Like, it's no big deal. Sorry. I probably didn't check out correctly when I went back to the thing. So git status and git log, actually. Yeah, better solution is the last one. So git add all. There we go.
Benchmarks.
14, part 1. Benchmark. I'm not going to say plural because there's only one of them.
Oh, well, there's one function.
Yeah, exactly. Not quite pluralizable yet.
Yeah, I have done this thing here. I admit, I'm guilty.
Yeah, I did the same, rm-rf, and then git clone again. Okay, my history is fine now.
Yeah. It happens. It happens all the
push
time.
-- force and clean up everybody else's history.
Yeah, that's great when that happens.
Do we want to take a look at part 2? I don't think we have time to do it because if I remember, it's tricky. Part 1 is done. Or do you think of some other optimization? Without a flame graph under the hands, I think there is not a lot.
Also, honestly, I wouldn't want to make like the most optimized solution ever.
Yeah.
So I'm more on, okay, if we are allocating like crazy and it's not the most automatic way to do that, let's try to fix those things. But I think now, at least for part 1, it seems reasonable. I don't see that we are using any clone or something like that.
Yeah, the only stuff is the vector of instruction in line 28 that we are materializing it. So instead we could stream through the input, the parsed input. Yeah. But again, nice.
Yeah, also it's not huge amount of instructions as far as I remember.
No,
right?
But it's not even giving you more performance, I think. It's just giving you less memory, but yeah, they are
594. It's not too many things. Now, if this were to scale for like some production system for AWS or whatever, then yeah, probably relevant. But for this exercise, I don't think we care too much. Yeah,
Let's jump to part 2 then.
Yeah, let's go to the README and see what part 2 is. Or?
I don't know if we will have a lot of time. We can probably start it, but the alternative is that we can also discuss the performance thing we did in the previous exercise.
Okay.
Maybe that's better, actually. Roberto, since you understand this one better than all of us, do you want to talk through it? Do you want to pull and share on yours, or do you want me to point?
You can go in the benchmark of exercise 13, or you can go in the folder of exercise 13 and run the benchmarks again. I created the benchmarks because last time we had the pull request on top of the exercise. If you want to do a pull request on top of our repository, feel free to do it. We are reading them, at least reading.
All right, so I'm running a benchmark in exercise 13 now.
By
Yes.
the way, it was Tommaso to send the pull request, so thank you, Tommaso, for that.
The current solution that we are benchmarking now, if I'm not wrong, is the one going through multiplying. Yes, you have to take a look at the last episode to have the insight of the algorithm. It's the part 2, not the part 1. Part 1 was the easy stuff. It's the part 2.
By the way, I think the idea was to talk about the optimization we did on this one. Or you did mean the previous one. Okay.
Yeah.
Cool.
Go to part 2.
Yeah.
Okay, on my machine was faster than that.
There it is. Well, your machine is fancier. Okay. Scroll.
I'm
going to close the terminal if that's okay.
Yeah, for the moment.
Get a bit more screen.
Basically, our...
let's explain the problem first.
The loop is the one... Well, if somebody wants to know exactly the problem, can take a look at YouTube for the last episode.
Yeah, that's fair enough.
But very shortly, we are looping on top of a vector. We are trying to satisfy some requirements that are in those vectors. When we find a requirement that is satisfied, we have to remove it from the vector. And going on what's left of the vector until this vector is empty. So we start in line 57 with a vector that is, while not empty, let's do something. And in line 68, we remove from the vector the stuff that we found as satisfied. So from the satisfied buses, we remove from buses. One day we will have an empty vector of buses, and we end the algorithm. The suggestion from Tommaso, if I'm not wrong with the name, was to use a partition. Partition is taking a vector and is giving back like a filter. Instead of discarding the other elements, is dividing them into stuff. The satisfied one and the not satisfied one. You can check out the PR if you want.
That's what I was gonna. I was thinking maybe we could.
Yeah, you can share.
We could check out the branch just so we can see the difference.
There is a way to check out directly the PR.
Mutable bus is the name of the branch. So let's go to that.
But I don't think it's in our repo, that branch.
Is it not?
No, but...
we have a PR. Let me share that.
Okay, I'll stop sharing my screen and you can share that then.
Yes, give me a sec.
This must be very confusing, I realize now.
All right, you should be able to see this, and I'm going to make it bigger, of course. Sorry about that. Right, so let's disregard all the stuff. But basically, I think this is the main point that Roberto wanted to discuss, right?
Yeah, basically that partition is doing our logic of buses that are satisfied by the candidate value against buses that are still not satisfied by the candidate value, and is dividing them in two. So with that line, you can avoid to do what we did, that was going through the buses, checking them, putting them in a vector, then taking them from the vector and removing them from the other vector. That is a little bit of memory management going back and forth. If you scroll another little bit below my comment, on line 66 there is the assignment. The new buses are the unsatisfied buses. I don't understand why this assignment works. So basically, probably because now basis is a reference to a mutable list. Because when I tried to do that, because it was my first solution to try to do that, I got some stuff like lifetimes and copy and references and the usual shenanigans around Rust management. But well, and like you said, the solution that was in main was running in 3.4 microseconds in my machine. For Eugen was 6 and something. Instead, this pull request is running in 8. Was running on 8.9 on my machine. To check out a pull request, you can write this, Eugen, or
using the GitHub or
Git.
Okay.
If you go in the repo,
yeah,
and you do a git fetch origin.
It'll give me the branch. Yeah.
No, it gives you the pull request because we are checking out the pull request, not the branch. But do you want to share the screen, Eugen, so we can go on?
Yeah, let me stop sharing.
All right, let me share, and then I need to switch over to the terminal. Share screen. Where are you? Rust Advent. There it is. Okay, terminal. Fake terminal. There we go.
Okay, git fetch origin pull. No, let me tell everything. Pull /6. That is the number of the pull request. /head colon.
Heads, uppercase head?
Lowercase head.
Okay.
Colon. Choose a name of a branch. Choose a name.
Okay. Whatever.
Whatever. Refactor, pull request. Now, git checkout refactor, if you're not already on that one. Git checkout refactor.
I'm not.
Git checkout refactor.
Of course, git checkout, because this one doesn't work.
Okay, now you are in a branch, your local branch, that has the same code of the pull request. If you go inside the exercise 13, part 2, you must see the partition somewhere.
Part 2.
Partition, there, line 62.
There it is.
So this is the code that is in that pull request. Now you can run from the folder, folder x13. No,
I'm not there anymore, of course.
No, if you run it from here, we'll run all the benchmarks of all the libraries that we have there, but let's just run this one.
Okay.
I don't care about the other
I'll run the bench now.
Yeah.
What? Because this one doesn't have the benchmark.
Okay, copy the benchmark from where you don't have them anymore.
I don't have them anymore, but I can copy the content of this file.
Yeah.
Main.
And then paste. Okay.
Paste over here.
Wow.
That's not how Git is supposed to work, but
no.
Don't tell anyone.
Don't tell anybody, exactly. Now try the bench. Oh my God.
It's fine. Sometimes the lazy solution is enough.
But well, for 1.5, yes, if they were a project.
Exactly.
Now it is doing the same warm-up and running everything and doing stuff. Let's see how it takes. Okay, on your machine is 26 microseconds. Is 300% more on the previous run.
So this is 26. Let me undo the changes. Save. This is going to be satisfied, unsatisfied. This is ours. Yours, actually. So if I run a bench now, this was 26.9.
Yeah, now
let's see.
But we have the percentage change, so it's enough to understand which is fast.
But I don't know if it ran here before. That's why I'm not sure what it's comparing against.
It gave you the number, so yes, you ran. I remember it, and it was like 6. 6.8.
Okay.
Yeah. So even if partition is way more idiomatic, for sure, because partition is even easier to understand. I mean, you have a vector, you split the vector in two, you multiply by the satisfied, you throw them away, and your basis is the one unsatisfied. Then you go on and go on and go on. The problem doing that is probably, at this point, I enter the realm of just supposition, of theories, is that is allocating way more. Because we have a vector, and we are removing from a vector. So the vector is always the same. We are just removing stuff from the vector. And Rust probably is smart enough to not deallocate memory or reallocate memory, just marking the cell as null or as not used and skipping it, basically. So probably the implementation of a vector in Rust is so optimized that keeping the vector and working on it is faster than generating new vectors every time.
Okay, so mutation is fast. Well, obviously mutation is faster, but
yeah, mutation is less testable, less bug safe, less what you want. But in this case, for example, is way faster.
Mm-hmm. No, that's
so yes. In this way, like you saw, guys, from that are following us, this is an easy way to benchmark stuff in Rust. You create your benchmark test. You use this criterion crate. You change your cargo toml just to say where is the benchmark to run. You run cargo bench, and it's doing. Also, is already doing not just one run. So it's not just one run. If you see, there are three numbers that are mean, max, and average. So it's giving you an idea. So if you have an algorithm that is very erratic, you can have a lot of standard deviation. Instead, this one is quite stable. I mean, from 6.7, 6.9 is quite stable. Obviously, they are very small numbers because those functions are doing not a lot. And the input txt is not huge. But still, you can get an idea of times. So, yes, basically. In this way, you also are able to check out a pull request that you have on your repository. You saw the command git fetch origin pull /did /head, and you choose the local branch name that you want. You go to that branch, and you do your stuff.
I never knew you can check out a PR directly.
Yeah, you can check out the code of a PR to test it, because otherwise, how can you test locally a PR?
No, that makes sense.
Because obviously the branch is not in the Luciano repository.
Yeah, it's
the
in
branch
the fork.
is in the Tommaso repository, is in the fork repository. Then when you do the pull request, Git is showing you the difference if you merge in the pull request. But the code and the branch itself are somewhere else. So with that Git fetch origin and the pull request, basically you are fetching the code just locally to you. So if you don't push again that branch to your repository, you will not have it remotely in your repository, but you just have it locally. That is enough to run the tests and test stuff.
That's what we want, yeah.
Yeah, and also here we run the benchmarks and to understand if it's better or not. I mean, from the idiomatic point of view, the partition is better and is also easier to read and so on. From the point of view of performances, the stupid solution, the naive solution that we come out with the first time was faster. And probably there is, if you start on that way and see what you can optimize, there are even faster way of doing that. I don't know, linked list. You start using a linked list, and when you have a satisfied bus, you just skip it in the linked list, because in the end you don't have to access a specific bus. You just have to scan them sequentially every time. So a linked list is more than enough. If you don't need to have the random access to a list, to a vector, having the linked list is probably more efficient to remove stuff from the list itself. But again, we can do. It's a good idea. Thank you for the suggestion to use the flame graph, because we can revisit even though those two implementation of the exercise 13 part 2 and see with a flame graph. Okay, where is this time coming from? Okay, the solution is slower. Our theory is that is memory allocation in the partition. So it's the partition itself that is slow, also because there is just the partition in that code. So there is not a lot.
So I'm thinking it could be cool if going forward, we'll save all the solutions that we have as like part 1A, part 1B, part 1C, and so on for however many solutions we have. So we can then more easily benchmark them in the future and look through optimizations and come up with new ideas.
I think we have all of them in comments. So yeah, we can extract them from the comments.
Yeah, but I was just going to be lazy and suggest we actually check them in as,
Yeah, we can do that with just changing names.
Yeah, exactly.
Cool.
But anyway, it's a topic for, well, next time we have a solution that we change.
Okay. This point, exercise square 14, part 2, we do that next time, Luciano. What do you think?
Yeah, I think so. We are already 1 hour and a half in the stream, and we generally do between 1 hour and an hour and a half. So I think we are on the long side of the stream already.
Oh.
So, who is doing the outro?
Sorry, I just lost sound for a second again. I think there's something really bad going on with my machine, but I can hear you now, so that's fine, and hopefully you can hear us.
We can hear you as well.
All right,
we say that we can close and wrap up.
Yeah, all right. So since we're wrapping up, then I should tell you that you can find the recordings on YouTube for both this. Well, this one's not there yet, obviously, because it's not finished, but it will be available on YouTube. You can see all the previous ones on YouTube. There is a link on the Twitch account in the About section if you want to find the channel. If you're watching this on YouTube, we do live streaming on Twitch every Monday, 5 p.m. UTC. Make sure to check out the Twitch link in the YouTube description and follow us so you can be notified for the next upcoming ones. Please leave us comments, leave us PRs. Any sort of contributions or ideas or questions are very, very welcome. It can only help us learn, and well, by sharing we can all learn, so that's nice. The repository is on GitHub, as you've probably seen earlier. Luciano, if you can put a banner of that, thank you very much. Everything's accepted. We're trying to learn Rust, so don't expect the solutions to be the cleanest or the most idiomatic, like we just spoke earlier. So once again, if you have any better ways of doing things, let us know. Feel free to open a PR and we can all learn. Once again, thanks everyone for the suggestions and collaboration. There was a lot of good stuff in the chat today and a lot of stuff that we have no idea about. So seriously, thank you for sharing all of that with us. It was great. On that note, thank you very much. And
at this point, send €5, not for the Luciano laptops, but for the Eugene laptops at this point, because, or at least an external USB audio card, something. a USB headset, something.
Yeah, I'll sort it out. Don't worry, I'll sort it out eventually. Cool. Thank you very much for watching, everyone, and see you next time.
See you.
Bye. Thank you.
Bye.